Hello everyone, my name is Betül and I'm a second year electrical and electronics engineering student in Bilkent University. In this video, I'll present you my Phys-212 modern physics project. The name of the project is the relativistic energy momentum relationship of beta particles. Our experiment discovers this relation through circular motion of beta particles in magnetic field. By comparing their experimental radius value with the relativistic and classical radii, we aim to determine whether the particles behave according to special relativity or classical mechanics. First, let me explain the theory. We start by equating the centripetal force and the magnetic Lorentz force acting on the particle. This gives us the basic formula for circular motion in equation 5. The expression for the radius is given in equation 6, where the radius depends on the kinetic energy Q and magnetic field B. With some simplification, we arrive at equation 7, which expresses radius in terms of momentum. For the relativistic case, we use the relativistic energy-momentum relation in equation 1 and apply it to the particle's momentum. This leads us through equations 8 and 9, and finally to the relativistic radius formula shown in equation 11. The radioactive source used in this experiment is strontium-90, and its decay energy is calculated using mass defect, giving us 546 kiloelectronvolts, as shown in equation 13. With the measured magnetic field of approximately 83.56 milliteslas, we plug in the values into our formulas and obtain that the classical and relativistic predictions for the maximum radius of the beta particles, which are shown in equation 15 and 16. Here's the schematic diagram of our experiment setup. To experimentally determine the radius, we used the geometric relation derived in equation 14 based on the steel collimator's geometry. We will compare the measured radius with the theoretical radii to see which approach is closer to the experimental value. The equipment for the experiment are 6 ferrite magnets, a radioactive source SR90, a Geiger-Müller tube system which we built for this experiment, steel capillary tubes for collimation, and an Arduino for Geiger-Müller counter. We also designed a housing for the setup and 3D printed it. So the complete setup looks like this. The housing and collimators ensure directional control of beta particles and reduce external magnetic field effects. We used collimators with the source and the GM tube. The GM collimator has an aluminum plate with a slit to improve measurements by minimizing the detection area of the GM tube. The beta particles were detected by the Geiger-Müller tube at 1 centimeter intervals from the source, and thanks to its Arduino compatibility, we were able to continuously measure and display the count rate in counts per hour. So it helped us to find the maximum trajectory of the particles, hence their maximum radius are obtained. Here's the plot of count rate versus distance. The peak appears between 8 and 9 centimeters, as you can see. The horizontal error bar on the red point shows the estimated uncertainty in the detector's position. The background radiation level is shaded in gray in the plot. It is centered at approximately 1115 counts per hour with its uncertainty range, and the count rate drops to background level around 8.5 centimeters. This point, d max equals 8.5, is taken as the particle's maximum detectable range. Using equation 14, we calculate the experimental radius as 4.15 centimeters, which can be compared with theoretical predictions. The experimental value is closer to the relativistic approach, as it can be seen here, which proves the idea that beta particles follow relativistic mechanics in accordance with special relativity. The experimental value is slightly larger than the theoretical value, however. There are several sources of error that may explain this discrepancy. First, the magnetic field is not perfectly uniform. It weakens towards the edges, as you can see on the magnetic field plot here. While we averaged values near the center to approximate uniformity, this may have overestimated the actual field strength. Since the field appears in the denominator of the radius formula, this leads to a lower predicted radius. A 5 to 10% overestimation in magnetic field can easily explain the difference. Secondly, the step size of 1 centimeter in data collection is relatively large. Finer steps like 0.2 centimeters might have produced a slightly smaller Dmax, and thus a smaller measured radius would occur. Thirdly, the lateral distance uncertainty of 0.25 centimeters also introduces a notable error. And lastly, some unwanted signals may have been recorded due to external electronic devices or accidental contact with the exposed GM circuit, even though the housing and the collimation precautions are taken. And these could lead to irregular counts and misestimation of Dmax. Despite certain experimental limitations I have just explained, our results clearly demonstrate that the classical model is not sufficient to explain the observed data. In contrast, the relativistic approach aligns much more closely with the measured data. In this project, we gained direct insight into how theoretical predictions can be validated with real world measurements through hands on experimentation and careful data analysis. This is the end of my presentation. Thank you for watching.